So the second part of implicit differentiation is inverse trig functions here. And this is extremely important because you see a lot of this in Cal 2. I really need you to memorize this one and this one. The rest of these aren't so important, but these two are definitely important. All right. You will see the others, but these ones I've circled here are the most important. So let's get started with this. So recall from trig, that if you have y equals inverse sine of x, this means that just sine of y is equal to x. This is what the book has, but let me show you a little something else. If you have inverse sine of a number, like for example, inverse sine of 1/2, inverse sine is just an angle theta, which when you take the sine of it gives you x. So if you have inverse sine of 1/2, for example, then this just means that there's a theta for which when you take the sine of it, you get a half. Now, inverse sine is only defined when theta is between pi over 2 and negative pi over 2. In other words, there's a bunch of thetas for which sine is a half. There's an infinite number of them, right? So we only look at the ones between pi over 2 and negative pi over 2. If you need to review this in trig, go for it. So we're only looking at this little area right in here. And so the inverse sine of 1/2, this would mean that theta would have to be pi over 6. The inverse sine of negative 1/2, inverse sine of negative 1/2, this is negative pi over 6 because that would be this one over here. All right, so I'll let you work that out in trig. Let's get to the calculus. So I want to find, so the goal here is to find, so it says if y is inverse sine of x, what is find dy dx, All right, so the derivative is going to end up being 1 over the square root of 1 minus x squared. It's this one here. So let's see how they get that. So I'm going to derive it for you. So what I'm going to do is I'm going to take the sine of both sides. So I get sine of y is equal to x. So the sine of both sides, the inverse sine and the sine will cancel on the right. This is assuming that y is in that interval that I just pointed out, negative pi over 2 to pi over 2. Because if you notice y is an angle here, sine of y is equal to x. Sine of y is equal to x. So y is an angle here. All right. So with that said, I want to find the derivative of y with respect to x. All right. So to do that, I use the chain rule. So cosine of y and then dy dx is equal to the derivative of x with respect to x is 1. So now dy dx is 1 over cosine y, which is, let's just leave it like that. So I want to go back to the very beginning here. Sine of y equals x, well, that's a triangle. Sine of y is equal to x, well, that's x over 1. So sine of y is equal to x over 1. So sine is opposite over hypotenuse. So when you do the Pythagorean theorem, this side becomes 1 minus x squared. Convince yourself of that. Just use a squared plus b squared is c squared. Pause the video and see if that's what you get for the horizontal side. So now, when I have dy dx is cosine of y is the adjacent over the hypotenuse, which is 1. So cosine of y is 1 square root of 1 minus x squared. So that means then that dy dx is 1 over the square root of 1 minus x squared. And that's how you get it. So if you have inverse sine of x and you want to take the derivative with respect to x, you get 1 over the square root of 1 minus x squared. That's what you have there. Now, that's what the formula was over there. Now, if you have the other case with tangent, the other one I want you to memorize if you say that y is inverse tangent of x, take the tangent of both sides. Tangent of y is x. And so when you take the derivative of both sides with respect to x, so this is what I'm doing. Let me do a different color. I'm doing d dx on both sides. So I'm applying it here and I'm applying it here. When I do it to the left side, I'm doing derivative of tangent y with respect to y times the derivative of y with respect to x. This is the chain rule because y is implied to be a function of x. Y is some function of x. I don't know what it is, but y is implied to be some function of x. Otherwise, taking the derivative with respect to x of tangent of y wouldn't make any sense. So what I'm using here is the chain rule. Chain rule. So the derivative of y with respect to it's df dy dx. It's basically the chain rule. And the f in this case is the tangent. So the first piece is secant squared of y, and then times dy dx. Okay, so I'm going to take what I had here, and let's put it together with this. So take the derivative, we get secant squared of y, and then dy dx is equal to, now the derivative of x with respect to x is just 1. So what we get out of this is dy over dx is just 1 over secant squared of y, which is 1 over, secant squared is 1 plus tangent squared. Y, we have tangent of y equals x. So if we make a triangle out of this, we get tangent of y is x. Y is an angle, so y is this little angle right here. X over 1. And so now this is 1 plus x squared here. And so what we get is equals, so we get equals to 1 over 1 plus tangent squared of y. Oh, I didn't need to do all that. But tangent of y is x, so it's 1 plus x squared, and done. And there you have it. So now here's the thing. With the chain rule, this is going to be just a little more complicated. So what I've just done is I've done these two here. I've done this one and I've done this one. Now that's it, just inverse tangent and inverse sine of x, but a lot of times it's not so easy, you see? So you have functions inside of them, inverse tangent of this mess, inverse sine of that mess. So it's really helpful if you do this with respect to the chain rule first to create a little formula. So let me write down what we had there before. So we had if y is inverse sine of x, this implies then that y prime is 1 over square root 1 minus x squared. And we had, now, before I get to the tangent one, now let's suppose that y is inverse sine of u of x. Well, let's just say u. And then u is some function of x. U is a function of x. So this, then y prime would be the derivative of the outside function times the derivative of the inside function. So 1 over the square root of 1 minus u squared. I'm just treating u like it's x, but then y, this is y prime, this is dy dx. All right, dy dx. So I have to go through u, so this piece is dy du, and then I have to multiply by du dx, chain rule. So times du dx, I'm going to write that as u prime. So in other words, this is equal to u prime over square root of 1 minus u squared. So to sum this up, if you take inverse sine of u, and you want to take its derivative with respect to x, assuming that y is a function of x, this is just u prime over the square root of 1 minus u squared. This you should probably memorize. Now let's look at tangent. So let's suppose that, suppose y is inverse tangent of u, and u is some function of x. So then dy over dx would be 1 over 1 plus u squared, because remember, inverse tangent of x, when you take the derivative, that's 1 over 1 plus x squared. So in this case, u is just serving as x. Now you multiply times du dx, right? So du dx would be just u prime. What we're doing here is this is dy du, and then this piece here is du dx. Chain rule, chain rule. So we get u prime over 1 plus u squared, and there we have it. So you should probably memorize this as well. So if you want to do an example of this, there are some good problems to do. Where are we at? Could probably do, let's do one that's not too bad. How about, let's do this one here, inverse sine of 2x plus 1. So then dy dx is going to be 1 over the square root of 1 minus, now x squared, this is serving as x squared, the 2x plus 1, so that's 2x plus 1 quantity squared times the derivative of that, which was just 2. So if you clean this up, 2x plus 1 quantity squared is 4x squared plus 4x plus 1. The ones will cancel and we'll get square root of 4x squared plus 4x. There's a 2 on top now. And now that denominator, you can pull out a 2. This is 2 over 2 root x squared plus x. Pull out the 4 as a 2. These cancel. And I get 1 over square root of x squared plus x. There you have it. All right, if you need more examples of this, ask, email me.